Okay, starting lesson 0.2, part B. Use the properties of radicals to simplify each expression. For part A, we could rewrite this expression as one radical of 12 times 3. Then we have the square root of 36, which is 6. All right. For the next problem, there are a number of ways to do this problem, but here's one way. I'm going to take the 3x squared and I'm going to take this radical here and use all these bits of information here to rewrite the radical as an exponent that's a fraction. So I know the root for my radical is the denominator for that exponent, and whatever I'm raising this quantity to, that's the numerator for my exponent. All right, so this is simply 3x squared to the first power, which is equal to 3x squared. Okay, so converting the radical into an exponent that's a fraction made this problem much easier to solve. On to the next example. Okay, we have the cube root of 16 over the 27. So I could take this fraction and break it down into the cube root of the numerator and the cube root of the denominator. All right, for the cube root of 27, that's easy. That's just 3. But for 16, we have to do a little bit of work. So I'm going to do a prime factor tree. The smallest prime that goes into 16 is 2. And I suggest starting with the smallest prime, and you'll see why in a moment. So we have 2 times 8, then we have 2 times 4, then we have 2 times 2. Okay, so the reason why we start with the smallest prime, because now notice that all the primes add up nicely like this. If you started your prime factor tree like this, sometimes there's potential to miss one of the prime factors. So if you write it out like this, they'll all be lined up nicely in a row at the end, and I think it's less likely that you're going to lose one of them. Okay, so you have the cube root of 16. We're looking for a group of 3. Pull out the 2, and we have the cube root of, we have a 2 left over, 2. And that's all there is to that. For the next one, once again, break it down into the square root of 75 over the square root of 4. Okay, then we have square root of 4, which is 2. And now 75. Once again, let's start with the smallest prime using our prime factor tree. 5 goes in here. Oh, no, let's go back. 3 goes in here. 25 times. And then you have 5 times 5. Okay, we're looking for a pair. I have a pair of 5s. So I'm going to pull out the 5. And square root of 3 is left over. And I'm done with that. On to the next example. Okay, for part C, I have to simplify this radical here. And the first thing I'm going to do is expand all the pieces inside. So I have 4 x's and I have 2 y's. All right. Since it's the fourth root, I'm looking for groups of 4. There's a group of 4. So I'm going to pull that out. And everything else stays inside. And I could actually take the square root of y squared and simplify that a little more. So I could do this. Let's not forget the fourth root. Now I could rewrite that, the last part, as an exponent, which simplifies to 1/2. Oh, that's not to the 4th power. Oops. That's not to the 4th power. That's to the 4th power. Still learning how to use this app. Okay, there we go. All right, and we have this. Now, this answer is still missing one subtle detail, and that's putting the absolute value bars around the x. Now, why are we doing that? It's a very subtle detail that often goes overlooked, but this is what makes the answer absolutely correct. Now, if x happened to be negative and you plugged it in here, well, the fourth power is going to make it positive. So your end result is still going to be positive. But if I plug it in here, my result would be negative at the end when it's not supposed to be. So to ensure that it continues to be positive, the way it would be just as if you plugged the negative in here, we're going to put the absolute value bars around the x to ensure that the end result is positive. Now, it's a very subtle detail that's often overlooked, and I won't hold it against you, but when you see it as a solution in your book and you're not sure why it's there, that's the reason. All right, on to example D. Going to do the same thing as the previous example. Going to expand all the pieces. So I got 8x's, and I got 4z's. Okay, I'm going to take the 160. I'm going to break that down, make my prime factor tree, starting with the smallest prime every time. Okay, I'm looking for a group of 5. There's my group of 5. All right, so I'm pulling out a 2. I have a group of 5 x's, so I'm pulling out an x. And that's all that I could pull out, so everything that's left inside is, let's see, we got the 5 left over here, and we got 3 x's, and we got 4 z's. Okay, now there's a reason why I will not be putting absolute value bars around the x here. And that's because if I plug a negative in for x here, it's going to become positive, right? Now, if I go to this solution, and I plug in a negative for x here, and I plug a negative in for x here, well, what's going to happen? The result here is going to be negative. Since it's a fifth root, the result's negative. And since I have a negative outside, that means the negatives are going to cancel out, and the result will still be positive. So plugging in a negative here, or in these values, still results in a positive result at the end. So there's no difference at the end, so that's why you don't need the absolute value signs. And that's it for that one. Okay, once again, the absolute value bars are a subtle detail. I won't hold it against you, but just be aware of why they're there. Next example. Alrighty, these are pretty easy to simplify. I'm going to take the 27, make a prime factor tree. Okay, I got a pair of 3s, so I have the 4 that I originally started with. I'm pulling out a 3, and I have a 3 left over. Then 75, starting with the smallest prime, I have 3 times 25, and 5 times 5. Alright, so I have a pair of 5s, and I'm pulling out a, well, not pulling out 3, I'm pulling out a 5, leaving the 3 inside, and I'm subtracting here. So first thing I gotta do is multiply these, so I have 12 square root of 3 minus 5 square root of 3, and then I have 7 square root of 3. Done with that one. On to the next. Alright, take 16, once again, prime factor tree. Be careful, notice that you're working with cube roots this time and not square roots. Often students overlook that important detail. Alright, so here I have a group of 3, pull out the 2, I have cube root of 2 left over. Alright, next one, 54, prime factor tree, 2 times 27, 3 times 9, 3 times 3. Okay, I have a group of 3, pull out the 3, and I originally started with the 3, don't forget that, and I have a 2 left over, so cube root of 2. All right, so I have 2 cube root of 2 plus 9 cube root of 2, which leaves me with 11 cube root of 2. Done with that one. On to the next. All right, rationalize the denominator of the expression, then simplify your answer. So what we're going to do is take this irrational number and turn it into a rational number by multiplying it by itself. Whenever you take a square root and you multiply it by itself, essentially the square root cancels out. And that's what's going on behind the scenes. So whatever you do at the top, you have to do at the bottom. Oops. All right, and then 5 goes into 5 once, 5 goes into 10 twice, so we end up with the square root of 10 over 2. And there's nothing else you could do there. For the next problem, we're going to have to multiply by the conjugate, because we have this expression with 2 radicals, and it's a sum, so then we multiply by the difference of those 2 radicals, once again known as the conjugate. All right, and then we're going to have to FOIL in the denominator position here. So on the top we have 3 square root of 5 minus square root of 6. On the bottom we have 5 minus the square root of 30, then plus the square root of 30, and then minus 6. And notice the 2 middle terms will always cancel out. And since that's always the case when you're multiplying by conjugates, you could, instead of multiplying everything out, you could just multiply the first terms and then multiply the last terms and just end up with 2 terms, and that's what you're going to end up with anyways. So we have 3 square root of 5 minus square root of 6, and then 5 minus 6 is negative 1, so our end result is negative 3 times square root of 5 minus square root of 6. Done. All right, for the next example, rewrite the expression in radical form. So it's simply 16, some radical, and then what's the root? Well, the root is whatever the denominator is, 4. And what do you do with the numerator? Well, that's what you raise the number to, which is 5. And that's all you have to do there. Done. On to the next. Perform the operation and simplify. Okay, first thing we're going to do is distribute this exponent, essentially. So we have x raised to the 4/3 power times y raised to the 2/3 power over x to the 1/3 power, y to the 1/3 power. Okay, applying some exponent operations here. Applying the quotient rule, I'm going to subtract these exponents. I'm going to subtract those exponents. So I have x to the 4/3 power minus 1/3 times y to the 2/3 power minus 1/3. So I get x to the 3/3 power times y to the 1/3 power. Then I end up with x times the cube root of y. Done with this one. On to the next. Reduce the index of the radical. Okay, well, how are we going to do that? Well, let's convert this radical to an exponent. So the root is your denominator. The number of variable that's being raised to a power, that's your numerator. So that's x to the half, essentially. So it's the square root of x. And typically you don't put that 2 there for square root of x. So we just have this. And for the last example, we have, I'm going to convert these radicals into exponents. So for the first radical inside the big radical, I have 10 a to the 7th times b, and that's raised to the 1/3 power then. And I'm going to take this radical here and turn that into an exponent. So I have 10 a to the 7th b to the 1/3. And then since it's a square root, it's essentially raising it to the half power. So then I have this. I'm going to multiply these exponents, and I have 10 a to the 7th times b, and it's all to the 1/6 power. Now I could rewrite this as a radical, and it's the 6th root. And then I'm going to expand and see, I have a group of 6 A's, so I'm simply going to pull out that A. So I have 10 AB left over, and no absolute value in this case, because if you plug a negative here, the result is not going to work since it's an even root, and so the same thing applies for this problem. And there's your answer. Done. Now begin your assignment on the bottom of the web page.